Hello everyone, what's going on? I'm Gaff, the Master 974 back again today, and Merry Christmas, because by the time this video is going to get uploaded, or at least published onto YouTube, it's going to be Christmas Day. So Merry Christmas, or Happy Holidays, whatever, all that good stuff. And what I wanted to do as a bit of a Christmas special for 2024 was to go back to a video I did quite a while back. And this is going back to May of 2022, believe it or not. And the video in question is how I was able to kind of backport the thermal discouragement beam from Portal 2 into Portal 1. And I'm going to be doing a sort of code review of what I did to make that happen. But before we get to that, I just wanted to give a bit of a preamble and an introduction as to why I chose to do this in the first place. So this actually was inspired by a comment that I received by a user named Detector, and they wanted to know if it was possible to change the colour of the thermal discouragement beams and make it so if you have certain colours combine into a reflective cube, then you get a colour that would make sense that as an output, and then a detector detects that colour basically. So the example they gave was if you had something like a red and a blue laser, then you'd have a purple laser as an output, and then there's a detector that detects a purple laser. And then if there's invalid combinations, then it defaults to a different colour. So that was their idea. The only thing that I saw through my research that even came close to making this a reality is the Portal 2 Community Edition. Now, I've wishlisted Portal 2 Community Edition for quite a long time, actually back in 2022. And you can see from some of the screenshots that they do have different coloured lasers, at least in one of the screenshots. Don't know if they'd be able to do the whole, combine multiple lasers into one and then change the colour and then have a detector that detects for that colour. So I suggested to them that they'd probably need to wait for that mod to come out to actually make that a reality. But the thing is, it's been over 2.5 years, the mod still hasn't come out. So I thought, you know what, back in 2022, I'm going to experiment around with this. Now, what I found in my research, because I think after this comment, there was a different comment that I needed to go to the Half-Life Project Beta website. And I didn't really check the Portal section because I've always gone to like the Half-Life 2 beta section. So I thought, you know what, let's just check out the Portal stuff. And it turns out that in the Portal section, there's actually a mod called Portal Project Beta. Now, I wanted to download it from the Half-Life Project Beta website, but it didn't seem to work. It would just make it partway through the download and then error out. But thankfully, the mod was on ModDB. And they even provided a GitHub link to the source code. So that was the first time I ever knows about the, Portal source code being available. Only the Portal 1 code though, not the Portal 2 code. I don't think that's available anywhere, or at least in its entirety. So using that, I decided to get to work on this thermal discouragement beam idea. So I guess when I made the original video about the thermal discouragement beam in Portal 1, I guess I wanted to make it so there was enough attention before I actually did a video showing how it actually worked. And the thing is, I believe I wanted to do this for the last Christmas in 2023, but due to IRL circumstances, I didn't get around to doing the video. I was on Christmas break from a job I absolutely hated working, and I just wanted to enjoy my time off and my Christmas. So that's why it didn't happen then, but now I'm in a much better frame of mind, and I thought, you know what, as a bit of a reward for the community, I might as well look into this now, otherwise I'll probably never get it done. So I'm in my Portal Project Beta source code, and over here on the server, I've got source files Portal, and I created a filter called Gareth test, and these are all the files that are going to be looked at today, because this includes all of the functionality for this discouragement beam, reflective cube, and detector stuff. So what I'm going to start with is the easy stuff, because the easy stuff is the reflective cube. So essentially in the .h file, I called it prop portal box.h, And then you do hashtag include cbase.h. That's almost always something you need to do. Then hashtag include props.h because we're going to be making this a physics prop, so we need to do that. Don't know if tier 0 memdb is necessary, but I'll just put that in there anyway. So created a class, cprop portal box. It's a C physics prop. That's what it derives from and inherits from. Then in the public section, declare class, cprop portal box, C physics prop. Nothing too complicated. Pre-cache and spawn. And then what I decided to do was make it so the box actually tilts a little bit. So my explanation for this is that you would want the box to tilt up a little bit to compensate for aiming the laser at a particular point. I think because the box kind of likes to wobble around a bit in Portal 1, so to have it sort of angled back when you drop the box, it sort of drops down forward in the direction where you want the sort of laser to be redirected to. So that was kind of the rationale for that. So the way that you can do that is to create a virtual ball called has preferred carry angles for player, passing through an input of a C-base player called *p player and set that to return true. And then create a virtual Q angle called prefer carry angles with void inputs, and then return the Q angle of what you want. So in this case, there's a negative 25-degree rotation in the x-axis, but nothing in the y or z axis. And then link entity to class. So you need to actually enter prop portal box in the Hammer editor or the developer console to create these reflective cubes, and it links to the class. So that's the header file. The .cpp file is not as intricate as the .h file, but again, hashtag include cbase.h. Need to include prop portal box.h. And also I added tier 0 memdb on here as well. But then in the pre-cache function, we just pre-cache the model, which is metalbox.mdl, and then call upon the base class to pre-cache. And then in the spawn function, just do pre-cache, set the model, add a spawn flag. So it basically means that you press the use key on the box and be able to pick it up and stuff. And then just call upon the base spawn stuff. So nothing too complicated there. It's pretty standard stuff. It's fairly straightforward. But what I'm going to get into now is the more difficult territory, shall we say. It's going to get a lot more complicated from here on out. So this is the header file for the laser, and it also includes the laser detector stuff, which I'll get to separately. So for the laser code, again, hashtag include cbase.h and beam shared.h because we're going to be using the cbeam class. So we need to, add that include, and also tier 0 memdb.h. Now, one of the things that I do here is add a spawn flag. I haven't done a tutorial about spawn flags yet, but it's not too difficult. But in this case, we're just creating a flag called start inactive and set that to hex 1. That's all that's really saying. So if that spawn flag is set, then the laser won't be active. But if it's not set, then it will be active. That's just the rationale for that. But then for the laser, it's just class CN portal laser. What does it derive from? It's a C-base entity. Then public section, declare class, usual stuff, declare data desk. We've got the constructor and destructor here, as well as pre-cache and spawn. And then the new stuff is a void function called beamThink, and then a C-base entity called draw laser from point, passing through a C-base entity called start entity and an int called beam number. We'll get to that. And then some input functions. I might have talked about input functions before, but we got disable, enable, and toggle. And then for the purposes of the detector stuff, which I'll get to, there's an array of beams of size 8. That's going to be accommodating for the redirected beams as well. Then an int called highest beam index, an int called env portal laser index, a vector called laser endpoint, a ball called m_b laser on, and in the private section there's an int called m_n site halo, a color 32 called laser color, and a float called m_fl next hurt time. So what's going on here, you might be wondering? Well, as I mentioned, there's the array of beams, which is going to be not only the main sort of beam that gets drawn, but also some of the higher order reflected beams. So that whatever the highest order beam is, that's going to get stored in this highest beam index value. Then the way I decided to work this, because the laser could have different colors, as you know, we've got the color 32 laser color down here, is what I decided to do was make it so a specific laser. How do I say this? So the detector has a certain number of an index. So you say it has a value of 1 in the detector code, which I'll get to. Then essentially this nth portal laser index would be 1 if this laser is meant to be the one that triggers the detector. So essentially it's if the number that's associated with the detector is the same as the number that is associated with the laser, then they're linked. So this laser triggers this detector, but it might not trigger a different detector. So if you have, say, 2 red lasers in one test, then you might find that one red laser might not trigger a detector that you might think it should. But if you have, say, a red or a blue laser in one test, then you need to make sure that the red laser is going to have an index that's the same as the red detector. The blue laser has the same index as the blue detector, I think, or whatever. I'm not sure about what I just said if I fucked up, but I probably did. But that's kind of the rationale for it. So it's just about matching the index of the laser with the detector. So that's how that works then. We have the laser endpoint, which is just the endpoint of the beam. We're going to need to keep track of that to see if the beam is within, you know, the boundaries of the detector. Then is the laser on? And then this N site halo thing down here, that's just for a little sprite to play on the laser. And then hurt time is just the damage in between, well, the time between taking damage from the beam. That's all that's really going on there. I'm not doing a good job of explaining this, I'm sorry, but this is just going to be where things get even more complicated because we're going to nthportallaser.cpp, and right at the top here I say that it creates a laser from the origin point of the entity to a point in a forwardly direction, but it can go through portals like portal 2. Maybe a detector too, so I was uncertain if I even wanted to go down the route of making a detector. And also a specialized weight box entity to handle reflections and multiple color inputs, which I'll get to. And I couldn't get it to work on the client, so I just stuck it all on the server because client stuff's difficult, you know. But in this case, we need to hashtag include cbase.h, nthportallaser.h, beamshed.h, ieffects.h, which we'll get to that. Then propportalbox.h, and then tier0mmdbegon.h. And right at the top here, we can see a couple of CUTL vectors. One is of type CNF portal laser asterisk. The other is of CNF portal laser detector asterisk. And they're called G_P total lasers and G_P total detectors, respectively. So if you don't know what a CUTL vector is, it's essentially a C++ way of creating a dynamically sized array. So if we go back to the nthportallaser.h code, you can see we created a static size array here of size 8. This means if you were to say try to create a 9th beam and add it to this array, then it's not going to work because the array has a fixed size. But in a CUTL vector, you can add to it or remove from it as much as you want, and it's not going to cause any sort of glaring issues. So in this case, we're going to need to keep track of all of the lasers and all of the detectors that exist in a map. Again, this could be very useful for, you know, making sure that a laser and detector are linked together. So if a detector has an index of 1 and the laser has an index of 1, then we can iterate over all lasers in the detector code at least to see if we come across a laser with index 1 and then we say that's the laser we want to use to check for to make sure that we did, you know, trigger outputs and stuff. It might not make a lot of sense. I'll definitely cover this again with the PhysGun follow-up video that I want to do in the future. But for the nth portal laser code, again, this is fairly standard stuff, just beginner data desk. I'm going to define the color and the env portal laser index as key fields. So this is something that you would need to specify values for in the hammer editor. But the color is a field, color 32, called laser color. And then the env portal laser index is a field integer. But then all of the other stuff is just defined fields. So that's like the sprite, if the laser's on, the highest order beam index, the endpoint of the laser, and the time it should take before the player gets hurt again. Then define input functions, all field void, disable, enable, and toggle related to the input disable, input enable, and input toggle functions. And then define a think func called beam think, and then end the data disk, and then link an entity to class. So the thermal discouragement beam is called env portal laser in the hammer editor and stuff. So let's just move on. So in this case, we get the constructor and the destructor. So when dealing with CUTL vector stuff, you can add by using something like, call upon the CUTL vector g_p total lasers, then do dot add to tail to add this env portal laser to the UTL vector. And then when it's destroyed, when the destructor is called, then you just find and remove this. So find and remove the laser from the UTL vector. So that's typically how you'd go about doing that. It's not a very good explanation, but sorry about that. Precache, need to precache the model that the laser is going to use. That m_n side halo, it is precache model of sprites light glow 03.vmt. Because we're on the server, we do need to specify the .vmt extension. We set the hurt time to be 0 so the player can get hurt immediately, then call upon precache. Then inside the spawn function, we call upon precache, call upon the base class to spawn the entity in. Then we check to see if the spawn flag of start inactive laser is set, and if it is, then we don't enable the laser, but then if the spawn flag is not set, then the laser is going to be on by default. Give a stock value for the endpoint of the laser, then iterate over all of the entities within the C-beam array from the header file. There's 8 of them, and just set them all equal to null to begin with. Then highest beam index is 0, so that's just going to be like the main beam is going to be index 0. And then we do set think of and cnf portal laser : beam think, and then set next think to GP global's arrow cur time. So now let's move on to the next function. It's a C-based entity called * draw laser from point, passing through an input of a C-based entity called start entity and int beam number, as you'll see here. So let's just get into this. So create a vector called forward, and then we do angle vectors of the start entity arrow get absolute angles, and then and forward, so that this value gets like set essentially correctly. Then this is done so we draw one beam only, so you can review this section if you want to. But if !p beam of the input beam number is invalid, so if this beam doesn't exist, then we create it. So we do something like this. C beam create, give it the material, give it a width, and then set the halo texture to be that size halo, set the scale, set the render color, set the brightness, set the effects, set the noise, the scroll rate, the collision group, but then finally we do point init of the start entity's absolute origin, then the start entity get absolute origin plus the forward sort of vector, and that's just like a temporary initialization of the beam. But then if the beam is valid, then we do p beam of beam number arrow remove effects of ef_no draw. That was just stuff taken from like how the portal turret handles the beam drawing stuff. Don't ask me too much about that in particular. But then we create a vector called origin point, which is the start entity's absolute origin. And then one of the things that I noticed is that when using the metal box in particular, that if you set the origin of the beam to be the center of the box, then when the beam goes through the portal, it doesn't actually draw the laser on the other side of the portal correctly. It's a bit weird. So what I figured out was that if you displace the start point of reflected beams by a little bit, then it fixes the issue. So we do a check here to see if the start entity matches the class of a prop portal box. And if it does, then we essentially multiply the forward vector by 20 units and then set the origin point to add on this little displacement. So that's all that's doing there. And now for the juicy stuff, because the way that a portal likes to do stuff is by using rays instead of trace_T's. So you got ray_T's instead. But what we do here is we raycast to draw the beam and get the endpoint in local space and not in an infinite distance that's, 1 dimension away from whatever, or 2 dimensions, whatever the case might be. Because I guess that's an issue that I was having, trying to get the endpoint of where the laser should be. But yeah, we create a vector called endpoint, a float called f_end_fraction, a ray_T called raypath. Then we initialize raypath with the origin point and then origin point plus our forward vector multiplied by some stock value like 8192. Then create a trace_T called tr. Then I add this, it's a C trace filter skip class name called trace filter, and it passes through an input of this end portal laser checked against prop energy ball and then collision group none. So basically, if there is an prop energy ball going along sort of the laser, then the laser's not going to get stuck on the energy ball. I guess that's what it's doing because it's skipping this specific class name. I think you're only allowed to pass through one class name as well. But then after that, we create a C prop portal called *p portal. And what is this? Well, it's a util function called portal trace ray beam. We pass through the ray called ray path. Then we do mask shot and trace filter and then and f_end_fraction. So what this does, as I say here, it's a preliminary trace to see if a portal is in the laser path. So again, it's starting from the origin point of the laser, going in its forward direction, and then this function returns a portal if a portal is hit, otherwise it returns null because you hit, say, a wall. But then if the portal is valid, then we set our endpoint to be the origin point plus forwards multiplied by 8192 units. But then this took me a little while to figure out, but the best function I found to use is util portal trace ray bullets of p portal, then ray path, mask shot, and trace filter and tr. So as I say here, we go through the portal if the portal's found, and then we do a secondary trace to obtain the endpoint of the laser in local space. Otherwise, if the portal is invalid, then we set the endpoint to be origin point plus forward multiplied by 8192 multiplied by this f_end_fraction variable, and then we just do a simple util portal trace ray of ray path, mask shot, and trace filter and tr. Alright, so moving on from that, what we do is we do p beam of beam number and then do points in it for actual, this time we do it for real with the origin point and the endpoint. And then we do p beam of beam number, arrow reeling beam, because we might change the start of the endpoint. And then what I decide to do is do laser endpoint equals tr.endpos, because we need to define the laser endpoint as the end of the trace, but we don't want to modify the endpoint variable as that's needed, so the laser actually goes through the portals as it's supposed to. Then here we do the damage stuff. So we do clear multi-damage. Then if the entity of the trace, so tr._pent, is valid, which it should be, and we are not a prop portal box, and we are not an end portal laser detector. So as I say in the comment here, if we hit something that's not a specialized reflective cube or a detector, then we want to dispatch effects. So this is where we do sparks. So if random int of 0 to 4 is exactly equal to 1, then we call upon g_p effect to do sparks at tr.endpos. Then if m_fl next to hurt time is lower than GP global's arrow occur time, then we create a C take damage info called damage info, passing through inputs of this 50 and damage burn. Then tr.m_pent dispatch trace attack, damage info forward and tr. And then set the next to hurt time to be the current time plus 0.15f. Then apply that multi-damage. And then if tr.m_pent is a BSP model, then do util decal trace of and tr and then red glow fade. Otherwise, if this condition is not met, then we just reset the hurt time. But then we return this entity, whatever it is. That is the sort of result of the trace. So this is where we get into the most complicated function of the laser code, which is the beam think code. So I have to say up front, this is a bad implementation of a recursive function. It's sort of like a yandere dev version of a recursive function, and you'll see why. So basically, if we have the laser on, then what we want to do is we want to create a C-base entity called *p hit, which is draw laser from point of this and then 0. So this is the main laser. If the laser's on, then this laser is always drawn. The highest index is 0 and it starts from the origin point of this, which is the nth portal laser entity. Then because this draw laser from point outputs a C-base entity, we keep track of what that entity is. Then what we try to do is we typecast the p-hit entity to a C-prop portal box by doing a dynamic cast. And then, as I say here, we set the highest beam index to 0. So what happens if the endpoint of this trace from draw laser from point just so happens to be a C-prop portal box, which is a reflective cube? Well, we want to do the draw laser from point function again, but we want to start it from the box entity and then increment the highest beam index value to 1. And then the same thing again. If that beam hits a box, then we want to draw another beam. So that's essentially what it's doing. It's kind of like a recursive function. I don't even go all the way with it. As you see, I kind of stop once we get to, I think this is beam number 5 out of 8. So it just goes to show how complicated this whole thing is. But really, that's all it's saying is if we have our laser and the endpoint of that laser just so happens to be another reflective cube, then we want to draw another laser from that cube and then increment the highest beam index. So that's what I mean about this being a little bit yandere devish. It's definitely not the cleanest, and as I say here, there has to be a more efficient way to do this. And then definitely here with the else statements, which is to say that if the box gets moved out of the way, and so the endpoint of the trace no longer causes this typecasting to work out properly at least, then we want to iterate from the current highest beam index number to the maximum size of the array, and then just remove all of those higher order beams, set them equal to null, and then decrement the beam index, and that's all these else statements are doing for all of the lasers up until, laser 0. Because that last else is if the laser's not on, then what we want to do is just iterate over the entire C-beam array thing that we created, remove all of them, set them equal to null, set the highest beam index to 0, and then we set next thing, and I decided to use tick interval because maybe I'm wrong on thinking this, but I thought that makes it update on a per frame basis, which might not be the best thing to do, especially if the game lags out really bad. So normally, as you see, I set it to think every 100 times per second. So that's sort of that initial situation, but I changed it to tick interval. As long as the game runs at a reasonable frame rate, then it should be thinking, a lot of times per second. Let's just put it that way. So that's probably the most complicated part of the laser code. So hopefully you followed along with that. Not that I explained it very well. But now you get to the input functions. So, they always have to pass through input data _t called and input data, even if you never use it. But in this case, disable causes the laser to be, well, disabled. If it's enabled, then we set, an M_B laser onto true and then call beam think immediately, so the beam actually starts drawing, and then create an input toggle, and then we inverse M_B laser on to set it to the opposite value of what it currently is, and then if it just so happens to be true, then we call upon the beam think function. So that was the laser code, everyone. Now let's get on to the detector code. So if we scroll down here, similarly to the laser, I add a spawn flag. So this checks to see if the detector should start inactive. And then getting into the detector code, again, it's a C-base entity. Do the declare class, constructor, destructor, spawn, and on activate is actually going to be the bulk of the code for the think function, but what actually ends up being the think function is this main think. Main think, as you'll see, is going to call upon onActivate, and onActivate handles all of the stuff that the detector is going to do. Then I create a function called cnv_portal_laser asterisk called find laser entities. Then, much like with the laser, we got disable, enable, and toggle as input functions. But for the detector, we're going to have output functions. So as I say here, for one laser input, we're going to have a C output event called M_N laser hit detector and M_N laser off detector. But then when we have two laser inputs, we want to check to see if laser 1 hit the detector, or if laser 2 hit the detector, or if laser 1 is off or laser 2 is off the detector, and then declare data desk. And lastly, as you'll probably see from here, there's too many booleans, but it's essentially what we need to do to trigger outputs preferably once. So we have a bool, which is M_B active. Is the detector active? Then are we detecting 1? Are we detecting 2? Has output 1 triggered? Has output 2 triggered? And then this third bool is just a stock name for ensuring that the outputs, especially in a 2 laser for 1 detector situation, ends up only causing the outputs to trigger 1 time. Then we create an integer called laser to detect. So remember earlier with the laser code, I said that there should be a match between the detector and the laser. Well, this is that parameter in the detector code. Then int laser to detect 2 and amount of lasers to trigger output. And then an array of cnv_portal lasers of size 2, because I only considered 2 lasers maximum for 1 detector, and you'll see why. And then, that's just saying find the nv_portal laser entity or entities that are needed to trigger outputs. So let's just get into the code, shall we? So here we, again, just do simple stuff. Data desk, key field, laser to detect 2, and amount of lasers to trigger output. So that's just, again, laser to detect should be, in a 1 laser situation, it should be whatever the nv_portal laser index is for the laser. So if the detector has laser to detect of 1, then the nv_portal laser index should also be 1. That's all that's really going on there. Then we define field, M_B active, is detecting 2, output 1 triggered, output 2 triggered, and third bool, all as field booleans. Define think of main think, define input funcs of disable, enable, and toggle, and define outputs of M_N laser hit detector as on laser hit detector. And you can see the rest of it. It's on laser off detector, on laser 1 hit the detector, and so on. So these over here is what you would actually use in the hammer editor to basically trigger the output functions. That's what it's doing there. Then link entity to class, nv_portal laser detector, and then cnv_portal laser detector. And then much like with the laser code, in the constructor, we add the detector to the CUTL vector of total detectors. And in the destructor, we find and remove this detector from the UTL vector of all detectors. Spawn function, base class spawn. If we're inactive because of the spawn flag, then we're not active. But then if we don't have that spawn flag set, then we are active. If the amount of lasers to trigger output is lower than 2, in other words, it's 1, Then we set laser to detect 2 to a null parameter to say that it's not used, even though it says null is 0 in this context. Then M1 score B is detecting is false, is detecting 2 is false, has over 1 triggered, no, no, third ball, no. P laser 0 and P laser 1, the array of the laser entities, are both null. But then we call upon the function to find the laser entities. And then down here, I don't think this stuff's necessary because I was experimenting with using the detector as an actual, prop, like a box, I think it was. So that's why it was, we got this set model of string get model name and set solid of solid v physics. But since I changed it to be more brush based, I don't think you need to worry about these lines so much. But then we do set think of and cn4 to laser detector, : main think, and then set next think immediately. All that's going on there. And so now we get to the find laser entities function. So it outputs a cn4 to laser asterisk. And so we create a stock array of input lasers. We set them to be null immediately. And then we iterate over all lasers from the CUTL vector, So by, to be able to do that, you need to create a for loop, start from index 0, go to lower than the count at increments by 1, and then input laser of 0 in this case is g_p total lasers dot element of I. So then this for loop would iterate over all of the lasers that exist. And at this point in time when I was doing this video, I didn't know why this ended up working, but I kind of know now. So what I say here is if the laser index does not match the detector index, then we exit out of the loop. And I thought it was contradictory, but it works because I was thinking that, the continue means you actually continue through to down here. But what it really means is we just continue on through the loop until we get the condition in the if statement to be true, in which case then it does go down here and then it breaks out the loop. So essentially what we're doing here is for our input laser, we compare the portal laser index to laser to detect and make sure they are equal to one another. And then when they are, P input laser is, this P laser 0 is the P input laser, and then we break out the for loop. And then in the event that we have 2 lasers, then we do the same thing again, but we just use P input laser 1 instead. Do the same thing, same check, compare input portal laser index to laser to detect 2. Then when they're exactly equal to one another, then we set P laser of 1 to P input laser of 1, and then we break out the for loop. And then we return both P laser 0 and P laser 1, which is not something that I thought you could do, but apparently you can. So in this case, P laser 0 should always be a valid entity, but P laser 1 could be null. That's just something that you need to realize. So now we get to probably the worst function of the detector code on activate. And you want to know why I'm not going to go down the route of creating a detector to detect 3 lasers? Well, this is the reason why. You'll see. So what we start with is by obtaining the bounding box of the entity. In this case, it's a brush entity. So create a vector called vmin and vmax, and then do collision prop arrow world space AABB of and vmin and vmax. So these vectors get assigned appropriate values. Then the vbox center is vmin plus vmax times a half. The vbox extent is vmax minus vmin times a half. And then we get the upper end of the bounding box by doing vbox center plus vbox extent. And then we get the lower bound of the bounding box by doing vbox center minus vbox extent. So essentially find the lower and higher boundaries of the brush, essentially is all we're doing here. Then if the detector is active, then if we have only one laser in play, so P laser 0 is valid, but P laser 1 is invalid, then we set an integer called index, which is P laser 0 highest beam index, C beam called asterisk P incoming beam, I think that's what that was supposed to mean, which is P laser 0 P beam of index. Then if P ink beam is valid, then we want to get the endpoint of the laser and determine the trigger boundaries. So we create a local vector called laser endpoint, which is P laser 0's laser endpoint vector, and then check to see if the laser is active by finding the m_b laser on boolean from P laser 0. Then if exclamation mark is laser active, so the laser gets disabled, then we fire the laser off detector output. Then we are no longer detecting. Output 1 has not triggered, and then we exit out of the function. Now, this is the way that it is because I didn't actually know of a way to check to see if one vector is within the boundaries of another vector, or rather another two vectors. So what I decided to do was deconstruct it down to the individual XYZ components. So all this is saying is if the endpoint of the laser is greater than the lower bounding box, but lower than the higher bounding box, then that means the laser must be within the bounding box of the detector. So if laser endpoint.x is greater than the bounding box, the low end of it, x component, but then the x component of the laser endpoint is lower than the high extent of the bounding box is x component, and so on and so forth for the y and the z components. So yeah, as I just said, all of this is doing is checking to see if the endpoint of the laser is within the bounding box of the detector. But if it is, then we are detecting, otherwise we're not detecting. Then if we are detecting and we haven't triggered an output, then we want to trigger that output. Then say that we have triggered the output so we don't end up going into this condition multiple times and triggering the output more times than necessary and then return from the function. Otherwise, if we're not detecting, then we fire the output to say we're not detecting, then we haven't triggered the output of m_n laser hit detector, that is, and then we exit out of the function. But now we get to a bit more complicated territory because what happens if we have laser 0 and we have laser 1? In other words, we have two lasers in play. Well, what I do here is we create a vector array and a Boolean array called laser endpoint of size 2 and R lasers active of size 2. And as I say here, we create an array for both beam endpoints and test to see if both are within the detector's bounding box. We create a for loop from, in index 0 to index 1, and then create an integer called index, which is P laser 0 or 1's highest beam index. So in this case, obtain the highest index of beam in play. 0 is the main beam, 1 is the first reflected, 2 is the second reflected, and so on. And then create a beam, which is P laser 0 or 1 of the P beam index. Then if that is valid, then laser endpoint of 0 or 1 is P laser 0 or 1 laser's endpoint, and then is the laser active? And that's based off of P laser 0 or 1. And then if P laser 0 is inactive, then what I decided to do was iterate over all detectors, and then detector is the element of the total detector's CUTL vector. Then if its laser to detect 2 parameter is exactly equal to the nth portal laser index, then that detector has its off detector output fired, but then it's no longer detecting. But then this specific detector is also set to not be detecting and has output 1 triggered is set to false. And similarly for if P laser 1 is inactive, then again iterate over all detectors from the CUTL vector, get the element. Then if that detector's laser to detect 1 parameter is the same as P laser 1's nth portal laser index, then that detector has its laser off detector output fired and then is detecting 2 is false. But then this specific detector has its detecting set to false, detecting 2 set to false, and then has output 2 trigger this set to false. Don't know if that makes no sense. I mean, in retrospect, I'm sure I looked at this before and thought, like, what kind of crack am I smoking when I came up with this? Because it kind of makes no sense, but I did it this way, so there's got to be a reason for why I did it. But anyway, carrying on. This is where we get to the long and nasty part and why 3 lasers isn't going to happen. So we create a local boolean called individual laser check is set to true, and then we check to see if both lasers are within the extent of the bounding box of the detector. That's P laser 0's X, Y, and Z components are greater than the low bound but lower than the high bound, and the same for P laser 1's endpoint. Again, the X is greater than the low bound but lower than the high bound. But if both lasers are within the bounding box of the detector, then we are detecting. Both of them are set to true. Otherwise, if laser 0 is the only laser that is within the bounding box of the detector, then we set B detecting 1 to true, but B detecting 2 to false, and then the individual laser check is false. Otherwise, if only laser 1 is incident on the detector, but laser 0 isn't, then is detecting is false, but is detecting 2 is true, and then the individual laser check is true. Otherwise, if no lasers are on the detector, then B is detecting is false, is detecting 2 is false, and the individual laser check is also false. So this is where the third boolean comes into play. That weirdly named variable, but it comes into play here. So if we are detecting both lasers and this third ball is set to false, then we have the laser hit detector, which was reused from the one laser situation, but in this case it's used to indicate that both lasers are incident on the detector. So we fire the output. We also fire the outputs for laser 1 and laser 2's hitting the detector. Then has output 1 triggered? No. Has output 2 triggered? No. Third ball is set to true. That way we don't enter this condition, numerous times when we don't need to, and then we return. Otherwise, if laser 1 is on the detector, but laser 2 is not on the detector, and we haven't triggered output 1 and the individual laser check is false, then what we do is we have the overall laser off detector output fire, but then we have laser 1 hit detector fire its output because that's detecting, but laser 2 off the detector because that's not detecting. Then has output 1 triggered is set to true, and the third ball is set to false, and then return. That way we can go back into this condition if laser 2 is detecting, but then we don't end up going into this condition a lot of times because now we set this has output 1 triggered to true. Otherwise, if laser 0 is not detecting, but laser 1 is detecting, and has output triggered 2 is false, but the individual laser check is true, then again, the overall laser off detector output fires to say that, the lasers are not on the detector, but laser 2 hit detector is the one that fires its output. But then laser 1 off detector, that has its output fired, then has output 2 triggered is true. Third ball is false, and then we return. Otherwise, if we are not detecting laser 0 or laser 1 and the individual laser check is false, then basically laser 1 off detector, laser 2 off detector, and both lasers off the detector outputs get fired. Then has output 1 triggered is false, has output 2 triggered is false, the third ball is false, and then we return. So that is really, 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 really complicated shit to try and figure out, but in the end that works. So all of these situations should only trigger outputs one time where necessary. But then we go all the way down here, which is that if we don't have any lasers for the detector to work, then we give the people that are playing the game a warning message to say that there's no valid lasers to trigger output conditions, and then we exit out of the function. I say here it's an extreme circumstance when there are no valid lasers in play to trigger detect outputs. So for example, that's if you have one laser and you give it an index of 1, but the detector, you give it an index of 2. And then, you'd end up in this situation because the detector thinks there's no lasers to trigger outputs. And then this else is all the way back up here for if the detector is not active. So we go all the way back down. So if the detector is not active, then if we are detecting, then we're no longer detecting. So laser 1 off detector, fire output. Is detecting is false. Has output 1 triggered is false, and then return. Otherwise, if the second laser is detecting, then laser 2 off detector, we fire the output. Then is detecting 2 is false. Has output 2 triggered is false, and then return. And I feel this should be first because it's, this is a 2 laser situation. If, laser 0 and laser 1 are detecting at the same time, then we do laser off detectors, fire output, but then set B is detecting to false, B is detecting 2 to false, has output 1 triggered to false, and has output 2 triggered to false, and then return. So in retrospect, that should probably go first, because if it is going to go through here, it's going to say, oh yeah, is M_B is detecting is true, so then it gets set to false. By the time you get down here, then none of this code is going to get executed. Maybe that was just a bad decision on my behalf, I don't know. But that's that function, and then the main thing, we actually call upon the setNextThing function immediately because there's returns in the onActivate function, and we basically need to keep the detector thinking, otherwise you can end up in a situation where you get stuck essentially forever. So you call setNextThing of GP globals arrowCurTime plus, and again I'll use tick interval here. Probably not the best thing to do, especially if there's lag. But then immediately after that, we call upon onActivate, which was that really lengthy function I just went through. And then here we go, we get the input functions disable. We just set all these booleans to false. Enable, we only set M_B active to be true, but then everything else is false, but then call upon main thing. And then input toggle, we inverse M_B active, and then set every other boolean to false. But then if that boolean check just so happens to enable the detector, then we call upon the main thing function. And that is it. I've been here for over 50 minutes, can you believe it, just doing this code review. I didn't think it would take this long, but there's a lot of stuff here. I wanted to try and explain this to the best of my ability. I might not have made that much sense, all things considered. But yeah, my throat's actually starting to hurt now as well because I've been talking for like 50 minutes straight. But I don't think I'm going to provide the code, but because of the speed and the pace that I went through this, you could probably put it all together just from watching the video, I guess. But yeah, that is the video, everyone, about how I was able to add the thermal discouragement beam into Portal 1. There are some issues. For example, if the beam is like going horizontally, but then it comes out of a portal and becomes, in a vertical direction, it doesn't hurt the player. So that's why when I did the video, I tried to construct the test chambers in such a way that you could actually get hurt and not notice that bug. Don't know why that happens. And yeah, there's absolutely no way I'm going to be doing 3 lasers for 1 detector unless there's a better way to do the check to make sure that the laser endpoint is within the bounding box of the detector. And even then, you've got to do all the other subtle checks for, laser 0 being within the bounds, or laser 1 being within the bounds, or laser 2 being within the bounds, or laser 0 and laser 1 are within the bounds, but laser 2 isn't, and it's all that complicated shit. And it's worse than this. Like, when all of this is bad, it only gets worse the more lasers you choose to add, unless there's a better way to do it. But yeah, that's the video, everyone. Merry Christmas. Hope you enjoyed it. Please let me know what you think. And take care out there. And I'll see you after Christmas for probably another video. We'll see. So, Merry Christmas. Have a great day. And peace and love. Take care out there.